Hey, hello everyone. I hope you had a great day so far. It was quite cold, so I appreciate you uh, coming to the class in this uh, weather condition. In last session, the previous one, we talked about the power electronic and why we actually like trying to like talk about the inverters and what are the significance of the inverters are in the power electronic. Yes. Not yet. Yeah, I will do that at the end. Uh, the lecture notes, the lecture notes regarding this is are posted. The PPT is not yet. Okay. So far we talked about the importance of the power electronics and inverter resources in the power system. Today we are going to start talking about the inverter itself, and we start to get familiar with the topology of the inverter and how they work. Okay, and try to like come up with the kind of like a theoretical model for that. That being said, as I mentioned in the first session, our class main goal is not to learn the theoretical kind of like concept. We are going to review the models and the equations, but they are basically the advantage of getting to know those equations is to like have another like a mathematic perspective beside the actual application and like the component uh perspective that we are gonna have. Okay. Now, is there any question before I start talking about the inverters from the previous session? No? Okay, let's just start then. The key concept of the inverters, okay, or in general term, the converters that convert DC to AC, the key concepts are rely on two main kind of like category. One is the waveform generation, all the concept that relies on waveform generation, which the topology of the actual switching device is within that category. Okay, and another one that we wanted to like talk about very specifically is pulse width modulation, okay, or PWM, which is basically a certain control system for that waveform generation. Okay, so one thing is to generate that AC form out of the DC system. Another thing is to control it in a way that you could handle the fluctuation of the loads and system. Okay, inverters basically have several type of topology. Okay, we could have single phase inverters. Okay, these are very basic kind of like categories for the inverters topology. We could have single phase, which is suitable for low power or driving facilities or driving applications. We could have three phase topologies. We are going to see later on why they are different and how we could like minimize the difference between the two topology, okay, by using a specific kind of like uh, configuration for our inverters. The next category is multi-level inverter. We are going to talk about them very specifically because these are the most important part of our course. Okay, when we talk about the inverters, we have single phase. There are tons of topology. We are going to talk about the details of that this session. Three phase is somehow an enhancement over the single phase. Okay, so there is no new theoretical kind of like technology in the three phase. It's the enhancement of that single phase topology into a three phase application. Okay, but multi-level are different. Not very much. Yeah, you not get completely new technology, but the way the controlling multi-level and the way and the advantage of the multi-level bring into the kind of like the applications are kind of like make them very special in the whole kind of like inverters kind of like technology. And we would have some functional also technology that they are like normally depends on the application. Like for example, the welding machine, okay, the welding machine is some sort of converters, okay? They are specifically designed for that purpose. So they are not a general topology of inverters. We are not going to talk about these functional, okay? But they are some sort of like inverters that are developed based on a specific application, okay? Now, these are the main categories of the inverters. But as a start, because the single phase inverters are the most simplest topology, we are going to focus on that. So we get introduced to the topic, okay, and then build on the understanding that we have for the single phase in order to understand, okay, what's going to happen in three phase or multi-level inverters, okay. Is there any questions so far about the types of the inverters and the category that I mentioned? No? Very good. So now let's start. There is two main topology in a single phase inverters, okay, that we normally use in order to convert DC to AC. One is called half bridge topology. Another one is full bridge topology. Okay. The half bridge topology, okay, consists of two switches that alternate between minus and plus DC voltage. So as you can see, we have one DC source. We use voltage dividers to shift the zero, okay, and have half of the DC voltage as minus value and half of them as positive value. Is that clear what I'm saying? Shifting the zero? Anyone understand that confusion? I don't want any confusion on that. So it's okay. So, and we using two switches to alternate between the positive voltage and negative voltage. And as you can see, when the top switch is on, our AC system is going to see the positive DC over 2 here. And when the top switch is off and the bottom switch is on, the AC system is connected to the minus value here. The half bridge alternate between positive and negative. Half bridge doesn't have zero. Okay, unless you shift the whole voltage. Okay, half bridge by itself doesn't have zero value. It alternates between positive half of DC and negative half of DC. Are we good? So this is you might think, okay, this is very simple topology, but that's it. The basic of the topology is that when you wanted to like develop your design or like analyze your circuit, there are some non-ideal condition going on through these switches and like these components, okay, that we are going to talk about that. But the basic topology is that simple. Okay, so do not overwhelm yourself or overthink about, okay, what's going to be the inverters, okay? So the most focus that we're going to have on inverters is on the control system. Because switches is just on and off, okay? And it's connected to the positive voltage and negative voltage in half bridge. But how to switch them and how to control that switching to answer the needs of the loads, that's the most important part. Any question about the half bridge so far? Are we good? Okay, now, the next topology, the second topology of the single phase are full bridge. This is the most useful one. This is the most simple one. Okay, if you wanted to like just have an inverter, very fast, very simple, low cost, half bridge is your answer. If you want a proper design, a proper voltage alternation, a better power quality, a less distortion in the voltage or harmonics as we defined that previously, we need to move forward to the full bridge. Now, full bridge doesn't need to divide the DC voltage. Okay, it relies on control of 4 switches, okay, instead of 2, 4 switches in order to alternate positive and negative voltage for the AC part. Okay, we are going to see how it works. Okay, now when the switch, let's say this is 1, let me number them 1, 2, 3, and 4. When the switch 1 and 4 are on, so S1 and S4 are on. You could see that the circuit between these two nodes, okay, here we have, sorry, this is not true. This one is this one. Here is connected to the positive voltage, positive end of the VDC, and this voltage is going to be connected to the negative one. So we have a negative VDC on our AC terminals. Is that clear? So by switching pairs of the switches, 1 and 4 works with each other, 2 and 3 work with each other. When you connect 1 and 4, okay, it would connect the minus voltage of the DC to the terminal of our AC system. When you turn off these two and turn on 2 and 3, now the positive one is connected to the base and the negative side is connected to the node. So now we have the positive value on our AC terminal. This is the basic kind of like configuration how the full bridge works. The full bridge is also, you can find with the name of H bridge, okay? And it's because of the shape, because it looks like an H, okay? So if you want to like search either full bridge or H bridge would result in the same kind of like topology. So this is two basic topology in a single phase, and this is very simple description of how they work. Okay, any question? Go ahead. What happens if 2 and 4 and 3 are on at the same time? Both terminals will be connected to the neutral, correct? So that's a very good question. Thank you for mentioning that. Okay, I missed that point. In full bridge, you can have 0 by turning on 3 and 4. Now, why we don't turn on 1 and 2 at the same time as 3 and 4? They are in positive, but there is another aspect of that. When you do the switching, we want to create the positive VDC, minus VDC, and 0 in like H bridge, okay? One condition that we have to always have in mind is that when you want to turn on the switches, you should avoid short-circuiting the DC voltage. That's your source. So whatever configuration of on and off on these 4 switches you do, you should never short-circuit the DC voltage. And that's another reason that why here both switches are not in half range, both switches are not on at the same time. Because if we short circuit our DC supply. Did I answer your question? Is that good? Yeah. Any other question? So immediately you can see by adding one leg to the half bridge and creating a full bridge, we already added another level of voltage as 0. And if you wanted to like mimic a sinusoidal voltage, you could easily see that this one is more closer to the sinusoidal, the pure sinusoidal, than that one. What that means? That means here we have less distortion from our desired voltage, less harmonic from would be injected into our system when we're using full bridge rather than half bridge. Are we good? Any question? The three-phase inverters are enhancement of that full bridge, half bridge. Okay, I don't want to like, go too deep in the details of that. We are going to talk about that later. Okay, but just for you to know, in order to create a full bridge out of the a three-phase system out of a full bridge, okay, you don't need 6 legs of switches. You only need 3 legs of the switches. Anyone can mention why? This is full bridge. This is not half bridge. It's three-phase, full bridge. Anyone can mention why in a three-phase, instead of having 3 full bridge, we have 3 legs of 2 switches, but still we have the full bridge kind of like advantages, like that 0 voltage. Anyone can mention one of the property of a three-phase system that help us on that to reduce those extra 3 legs? In three-phase system, search on that, okay? If you are not completely like is not top of your head, search on that. In three-phase system, we had 2 configurations. Star configuration, okay? Delta configuration. What was the difference? The difference between the two was in a star connection, we don't have a neutral. Okay? So, same concept. The same way that in delta, we deleted the neutral, okay? With the same concept, we don't need those 3 extra legs. Instead of providing phase to neutral for each leg, we are phase to phase. So we have 3 phases fully applicable. And when you wanted to like create each of those phases, you basically use 2 of the legs. So for example, like let's say this is AB. It's a full bridge. AC, still full bridge. BC, still full bridge. Is that clear? How we get that? So no, I don't want to like go deeper than that. I just want to like represent the 3 phase just for you to like get familiar with the idea. Okay. Now, any question? Let's talk about the most important, the multi-level inverters. Okay. We have 3 main category of multi-level inverters. First of all, anyone can suggest, based on the name, the name is multi-level inverters, okay? Anyone can suggest what is going to be the difference of a multi-level and a single phase. What is your guess? What would be the difference between multi-level inverters and a single phase like full bridge inverter? More than 1 volt. Multi-level inverter, as an inverter, is a 1 inverter. The topology is different. Okay. When we talk about the half bridge, what we had in half bridge, at the output of half bridge, What we had? Positive, negative, positive, negative. Too low. Two-level voltage. So if I want to say I want multi-level inverters, what is the guess for you? What is the difference? It's gonna add more steps. You are gonna have the ability to create more level, for example, of voltages, and by controlling those on and off switching like times, you can pretty much mimic a very good sinusoidal. Now imagine those steps are smaller and smaller. You know how the differential, how like the summation goes to the integral? If you make those steps smaller and smaller, more steps, you basically are limiting, like going toward a pure sine. What that means, you are reducing the harmonics, which are a big deal in renewables and inverter-based system and power electronics. Okay, so now we have three type of multi-level inverters. Okay, I'm going to introduce them, but we are going to only use one of them. Okay, the first one is diode clamp. As you can see, the configuration uses the ability of the diodes as a unidirectional kind of like device and the switches to have a certain topology in order to create those level of the voltages. So for example, they would the control system would turn on and turn off, give a configuration of on and off to all those switches in a way that the diodes would split up the voltages to create multi-levels on top of each other by allowing the current to go past or blocking the current. Okay. The next category is flying capacitor. Still a switching device. This one uses several capacitors in a specific topology in order to kind of like use the same idea of like voltage division when you want to like divide the voltage using capacitors. Okay, it's kind of like the same idea, but using that kind of like application of a capacitor, combining with the switching algorithm, they create levels of, well, you could imagine that the levels of voltage adding up. Okay, so and create multiple level. And when I say multiple level, like for example, like if this is 1 volt, if these two comes, it gets 2 volts. So you have 1 volt, you have 1 volt, and then 2 volt, and then 4 volt, and then 8 volt, and then you could come down, step down of the voltage and create the multi-level inverters. The third one is the cascade H-bridge. Okay, and the way this one works is that you remember that full bridge that we had that could give us 3 level of the voltage, positive VDC, 0 and minus VDC. Okay, now we are gonna cascading them, connect them in series, and turn them on and off. And because they are connected in series, the output voltage become the addition of those. So we could control how many voltage, what is the voltage of each step gonna be. Is that clear? So we are cascading those full bridges. So you have like one full bridge that is like this. Oh no, not this. Sorry. How can I redo that? Control V? No? No? Okay, I'm gonna draw this. This is not good. Okay, another one. This is my full bridge, one full bridge. This is, don't do that. This is another full bridge. And when I add them together, up to here I have 0, then here, then goes one level up, one level down, 0, down, down. You see the process when you're cascading those H bridges. Now, we are gonna focus on one of them, and probably you could guess which one. Any guess? Which one is the most advantageous one?
I said diode clamps.
Why? Why do you think like the diode clamps is the most advantageous one?
I said diode before you said that part, so I don't.
Oh, okay. So yeah. So that was this is like when you hit the buzzer before the question is finished. Yeah. So what do you think? Which one of these three categories are the most advantages that we have to like focus on? Gives us a better edge of like technology. It's a better engineering solution. The H bridge. Why? Exactly. Yeah.
Oh,
No. Add something. Yeah. Go on.
I think it was the H bridge because bring these hits.
Can you explain a little bit? I didn't get your idea. Sorry.
So when you're talking about which one like has the most advantages, I'm assuming like they all have their advantages. I'm assuming in Chrome that we're working with being converted like, renewable energy to AC. It says like cascade H bridge, can achieve much higher voltage levels. So I would assume that if you're converting DC to AC, you wouldn't want to be topped out by using something that's, I would say, just underdeveloped for the application.
That's true. All of them true. Now let's me to like restate what you said, okay, and add a little bit of like other aspect of engineering labor into it. Okay, so first, the reason that you mentioned about the high power and the stacking of the voltage and like high performance is the reason actually is the advantage of the multi-level inverters compared to other type of inverters, the single levels or like two levels, single phase, three phase. Okay, why? Because now you have multiple technology, multiple modules of inverters, so you could reduce the voltage stress because they are in series. Each of them, each of those modules, each of these H bridges, okay, face lower voltage stress. So now the whole system could go in a higher level. Do you remember one of our difficulties or challenges was that the semiconductor devices are very sensitive to the voltage stress. We mentioned that in previous session. Remember that? So now you could do that. And because it's, again, cascaded, okay, you can provide higher power with lower current. And what the lower current means? Less heat, which was one of the biggest challenge that we had dealing with the semiconductor devices. So that part is the general advantage of the multi-level inverters against the single phase or two phase or all the other kind of inverters. Okay. Now, why H bridge? You chose the right one. Why H bridge? Okay. Let's talk about in reverse. Why not diode clamp? We mentioned one very bad characteristics for diodes in the previous session. What was that? What is the bad characteristic of diode? Go ahead.
Doesn't it only flow one way?
Either way, if you have a switch, you want to have it one way. You want to like have the direct one way. When you compare diode, like for example, to the MOSFET or IGBT or BJT, what was the disadvantage of the diode? You can control it. You know, any fluctuation, you have to see, okay, what's gonna happen. You don't have any control. So you just have to like stay and pray to say, okay, nothing happened. You know, so diode is off because it reduced our ability to control the state of our system. Now, why the capacitor, blind capacitor should not be a good idea. Remember, you're an engineer. Anyone can guess why we ruled out like
Would just be like hard cost, let's say.
cost. We are engineer, we are very good people, we care about the technology and well-being, but we want money. Okay, we are doing it for money. So if we can do it with a cheaper component, why bother to have like the most expensive component in our topology? And we're talking about the power scale, not electronic scale. In the power scale, the capacitor are not like $50 or like $2 each. You know, the capacitors in power are very expensive, extremely hard to work with, extremely unstable. Any fluctuation could explode a capacitor. Okay, so as much as we can in power, we want to avoid them. They are not a good engineering choice for power engineering. So all these together would rule out these two categories of multi-level and bring us the choice to use Cascade Edge Bridge. And you are going to see how beautiful the control system in Cascade Edge Bridge works compared to other. And as you can see, we already talked about that. The multi-level inverters reduce the harmonic. We already visually could see how it's reduced the distortion from the desired waveform that we want. Okay, is more closer to sinusoidal. We have higher power quality. We have higher power application because we reduce the voltage stress. With the same current and higher voltage, we can provide higher power. Okay? Any questions so far? No? Now, let's talk about a little bit of math perspective of that components. I'm going to talk about the half bridge because I don't want us to like have a crowded kind of like a scam here. So, but I know you could understand that like in the half bridge, moving toward the full bridge or multi-level is just adding another component to the same model. It's just adding 1 kVL to the equations or 1 kCl to the equations. Okay, so it's not going to be a big deal. So let's talk about the topology. Do you remember that I told you that like in half bridge we have 2 switches for on and off? Now, the true category is not that simple. For each switch, you need a reverse diode. Why you need a reverse diode? Here, why you need a reverse diode? Anyone can tell me? Like why? If you eliminate those diodes, what's going to happen? Think about it. Like, let's say these diodes are not here. If you turn on the switch, what's going to happen? That diode that you're talking about is the Snowbird diode. That now we are not talking about that. Okay, we are going to talk about that. The Snowbird this is one of the application, but you have a DC circuit and an AC circuit. And when you talk about the transferring energy, the basic concept is that, okay, your circuit should be closed. If your circuit is floating, you don't have any energy to transfer. So just the switch cannot provide that. As you can see, like for example, when the top switch is on, the bottom diode would close the DC circuit. So the actually flow of energy would happen. And vice versa. When the bottom switch is on, the top diode would do that. That's the very basic one. What your friend mentioned about the reversing current, we are going to talk about that when we want to talk about the non-ideal cases of the non-ideal situation. When we talk about these inverters, that actually we mentioned that those when you turn off the switch, it not immediately go off. It needs time to go off, and by time that means it cannot reduce the current from like I to 0 immediately. There is a time gradually would go down to 0. In both all the semiconductor, it doesn't matter if it's a diode or IGBT or MOSFET, all of them has that kind of like non-ideal condition. And if you have a reverse current, what you should do for it, you can't just let the reverse current go through your circuit haphazardly. It's a protection issue. You have to drive a snubber circuit to absorb that reverse current and kind of like try to like dissipate it through loss and resistance in order to like control it, so it not flow through your actual circuit, your main circuit. We are going to talk about that later, okay? So it's number one. When we are talking about the soft switching, we are going to talk about that later. But that was true. I wanted to commend you for that, but it's for a little bit later, for more advanced kind of talks. Now, when you look at this, we wanted to model what's going to happen in half bridge. The current that goes to the AC in the positive half cycle, is going to be, you could see here, the positive current is the current passing through the Q1 minus, this is KCL, minus the current that goes back to the diode. Is that correct? It's KCL in that node. We would have the same KCL here in that node to model the negative part of current. I positive, I negative. Are we good so far? This is the start of our modeling. Now, when we are in a positive half cycle, if S1, the top switch, or Q1, okay, is 0, D4 is going to be on. So this is one situation. This switch is off, and this diode is on. This is one situation that could happen. Okay, what's going to happen? If you do the KVL, you could see that the voltage, this is off, so this is off, okay? The terminal voltage, because of this diode, will connect to the minus VDC over 2. Now, on that part, if S1 is on and D4 is off, sorry, it's a typo here. Okay, we are talking about the positive half cycle. So if this one is on, this one is off, this one is on, we have minus VDC over 2. If this one is on and diode do not carry any current, the terminal will connect to the positive DC. Are we good? This one is on, so there is a short circuit here. This one is off. This one is already off because we control it. So there's an open circuit here. and short circuit here. So the terminal would connect to the positive voltage. Are we good? So you could see here, S1 is off. D4, I have to like do the typo here. Diode is on, minus DC. S1 is on, diode is off, plus DC. Okay? Same goes for the negative half cycle. Now, Q4 is on, and this diode is off. So this is off circuit, this is open circuit, this is short circuit. Terminal connect to the minus DC. If this switch is off and this diode is on, this is open circuit. Okay? This is short circuit. So the terminal connect to the plus DC. Do you see how it works? Now, why these two cannot be on at the same time? Or these two can be on at the same time? Because as you see, we are only like doing like a cross connection. Like this is on, this is off, this is on, this is off. We always why these two cannot be on, or these two cannot be on at the same time? Why we ruled out that conditions?
Because if they're all on at the same time, plus it's.
If all of them are on, it will be short circuit. What I'm saying is that why we cannot, like this is off, but these two are on at the same time. Why is not going to happen? So there is no short circuit because these are off. Okay. But why these two cannot be on at the same time?
When the current just go the diode.
Let's think about that. Okay. When this is on, what is the voltage here?
It's the positive.
No, here, between my fingers, between these two nodes. If this is on, what is the voltage across the switch? When it's on,
It's just, it doesn't change.
it's zero.
Yeah.
If the voltage here across this switch is zero, that means the voltage across the diode is zero. What happened then?
Nothing.
Nothing. Diode would not flow because the voltage is zero. We learned that. You remember the two type of like silicon or germanium diodes? They need at least like 0.3 voltage to conduct. So if it's less than that, diode is open. So it cannot be on at the same time this would be on. Because if this is on, immediately, like it's default, this goes off. Same goes for you. Is that clear? No. Any question? This one, if the switch is on, this is the ideal switch. If the switch is on, that means this is short circuit. Correct? So if it's short circuit, that means these two voltages or these two nodes have the same voltage. So across this diode, the voltage is zero. Did I answer your question? Is that clear? Any other question? Now, when you do the half bridge, by turning on and off the switch S1 and S4, or like this top switch and bottom switch, okay, you create a voltage alternating between minus VDC over 2 and plus VDC over 2. That we already gone through. Okay, now you can control when to turn on and off those switches. Each alternation is one cycle. So you start from here to here. When you come back to this point, that is one cycle. The definition of the cycle in alternative voltage or current. Okay, so we call it the one cycle period. or T of S, we define another value, duty ratio. We are going to use that later on. Duty ratio as the ratio of positive to the whole cycle. The width of our positive voltage to the whole cycle. And we call it duty ratio, or D. Is that clear? So DTS over D is going to be our duty ratio. Any other question? Any question so far? We are just gonna, so far we are just went over how they work and how the topology is working. No? Now, let's talk about in more detail. We already said that when we have like a half bridge, the positive current is going to be the current of the switch minus the current of the diode. Same, the negative current is minus current of the switch plus current of the diode. It's because of the reverse direction, okay? We stick with one direction, the negative part. The concept is the same, but because we are using one as a reference, the other one, the minus changes, okay? So it's basically minus of IQ minus ID on the negative part, okay? So it's like something like that. Now, when S1 or the top switch is on, okay, the upper switch cell is closed and the lower one is open. Therefore, the terminal is VDC over half. The positive current is equal to the current of the DC, okay, and the negative current is 0. Same goes for the other half cycle, for the negative one. When the bottom switch is on, the terminal is connected to the negative one. I have a lot of typos. I have to check this. To the negative voltage, the positive current is gonna now is 0 because the top switch is off, and the negative current is equal to the current of the DC. Okay, which is the current that goes through the bottom part of the system. Now, we know that the time function of S1 plus S4 through the time, they are completing each other. You see here, S1 and S4 completing each other because they are, when this is 1, this is 0. So they all together, S1 plus S4, okay, the time on and off, the time function that describes the on and off of the both switch together is equal to 1. This is going to be always not. Is that clear? See? The summation of the two, let's create the summation here. From here to here, because S4 is 1, it's 1. And from here to here, because S1 is 1 and this one is 0, is still 1. So it's going to be always 1. S1 plus S4, the time function, is always 1. And V of t, the time function of our voltage terminal, is going to be positive DC voltage times S1 minus DC voltage times S4. Is that clear how we reach that? So when S1 is on, when the top switch is on, okay, S1 is equal to 1, S4 is equal to 0. So the terminal voltage is going to be the positive value. When the bottom switch is on and the top switch is off, S1 is 0 and S4 is 1. So the terminal going to be minus the DC value. So this is the function of the time function that we could describe based on our DC voltage and our on and off situation for the two switches that we have in our half bridge. Now we have a function, an alternative function for our voltage at the terminal. Is that clear? Any question? No? Now, the positive I through the time is going to be the DCI times S1. The negative one is DCI times S4. Is that clear how we get there? This is a time value. If the S1, if the top bottom is 1, S1 has a value of 1 on that duration of time. That means the positive current equals to DC current. And if the bottom switch is on and the top switch is off, this is going to be the value of this S1 is 0, the value of S4 is 1. So now IP is 0 and IN, the negative one, is DC current. Are we good? Is that clear? Any question about that? I'm trying to create time functions for the variable that we wanted to discuss about. Are we good?
So for S4, so that switch is on, it's the negative DC, right?
Yes.
Negative.
S function itself has a value either 0 or 1. So the S function for switch 1, which is the top switch, if it's 1, that means the switch is on. If the switch is off, it is 0. Same goes for the bottom switch, which we show it like S4. Okay, now by this function, by this time function, we could bring all the cycle together in one function, in one time variant function. Because when the top switch is on, this is 1, this is 0. So we would have positive VDC. Now we have this function that we created. Now could be described through time. Are we good? Any other question? Anyone knows why we gave us a hard kind of time to actually why defining the voltage or current as a time function? What's the benefit of that? This is not about the inverters. This is a very general question. Why we need time function?
It's gonna check.
It is going to change. When we say it is going to change, I'm going to kind of build on your answer. Okay. Everything that we face, okay, in engineering, is a dynamic system, and dynamic means change. And how we could observe change is through time. So if you wanna model any kind of system, you need to be able to analyze the system behavior, meaning the system's change through time or response of the change through any input through time. So the time function is basically in a mechanical engineering kind of concept, okay? Is the way of analyzing or modeling any type of parameters so we could predict what's going to happen later, or we could find out what is the fault or what is the state of the situation right now. Is that clear? So, okay. So when we talk about the voltage, is not that much of a difference when we talk about the potential energy in when you throw a ball, same concept, basically. Same laws. Now that we have time function for our variables, we could get rid of those diodes and switches and have a electrical like AC circuit analysis models, very simple with basic components. As a model of that switch, we have voltage DC, we have current sources that inject that current IN and IP, and they are function of time. We know how they work, when they are 0 and when they are I. And the voltage across the terminal, the voltage of the terminals, which is from 0 to that terminal, okay, is going to be, again, the function of the time that we define. Now, I want you to let me know why both these points are 0. I want to ask you, this is a very general electrical circuit analysis question. I have two currents flowing here. I have DC sources here, and my terminal is here, not here, here. Okay, why the voltage, the node that connect the positive and negative voltage, the currents together, so basically collect the currents and direct it through the AC system, okay, has the same voltage as 0 voltage in the middle of our DC source. I want you to think about that. This is not a question about the inverters, okay? What I intending about asking that question is to trigger your curiosity. Okay, just because I show you this picture, you shouldn't accept it. You should question it. Okay, this is a true. I don't want to like say this is a faulty graph. This is a true model. Okay, this is accurate. But what I want you to develop is questioning everything. Why is that? Why is this way? Why is that way? Try to like think like this, okay? Otherwise, you don't practice critical thinking. Okay. Now, to answer, what is the characteristics of the current source? You had a. Let me rephrase my question. We had a bunch of important parameters in AC circuit analysis. We mentioned that in the first session. What was the 4 basic parameters?
Voltage, phase, power.
Current, voltage, phase, power. Okay. In power source, let's skip the frequency and the power because in the sources, because we control them. Okay, the variables are in the sources, either voltage or current. The variables are voltage and current. The other two we decide. Okay, what is the characteristics of a current source in terms of voltage and in terms of current? What is the voltage across a current source?
0.
0, because it's a current source. So the characteristics of current source is it has its current defined. The voltage across it is 0. For voltage source, it has its voltage. Okay. What is the current? I want you to say 0. It's not 0. It's dictated by the circuit. Are you good? Now, do a KVL here and find the voltage here. Positive VDC. Opposite VDC here, 0, 0. Difference between here and here is 0 voltage. Are we good? So that's why we have this. And that's why, so this is the ideal case. Now we have this node to collect the current of positive and negative passes. And we model the voltage that it creates at the output with this voltage. So now the KCL here would add up IP and IN. So we have our I of terminal and we have our voltage of terminal here. And we know that voltage of terminal, we already have the function. IP and IN, we already have the function. Okay, so what's going to be the I terminal? IN plus IP. Yeah. Are we good? So when we talk about, now that we have our electrical model, now we could talk about that third important problem that I said, power. Yes, power. Now, we have the DC side power, which is the power of the negative part plus power of the positive part. The power of the negative part is the voltage of the source times the current plus the voltage times the current for negative part. So we have our power, the DC power that is supplied to our system as a function of time. Because although the VP are DC, the currents are function of time. Are we good? So, what is the power of terminal? Voltage of terminal times the current. Same formula. Now we have the power of the terminal based on the time. Power of the AC part is not important, but you could also practice that too, like calculate that too. No, I don't want to, but I just mentioned. Now, we have a DC power that goes through our switching, our half bridge, and we have a terminal power that get out of our half bridge to our AC system. Okay, so the difference between the two should be whatever is lost here. Is that correct? Are we good? So what is the P of DC? This one minus this one. They look the same. So it's 0. Why? Because we are still on ideal model for our switches. We didn't consider an ideal situation for our switches. Are we good? Any question? Power of the AC system, whatever goes to the AC system. Any other question? In case of non-ideal situation, yeah, we are going to talk about. I don't think today I'm gonna get to that point, but we are going to talk about it actually. Like, this is the non-ideal model. We are going to get to that. Okay, when the switches are not ideal, they have impedance in it or resistance in DC part. When we talk about, and they have voltage drop. They are not short circuit. Okay, and since they have resistance and voltage drop, that means they have loss. Okay, and we are going to talk about those. Topic 2. Now that we have voltage and current as a function of time, as I said, like in any type of mechanical system or dynamical system, we could analyze, okay, the behavior of our system based on differential integral function that we have, or ODE or PDE of the function that describe the system. Now, what was our system? Our system, we had an inverter that had V of t and I of t as its variable. I don't care about these parts. So far, this is our system. I don't want to like get into that. And I could model the transmission, the terminal, with the resistance and inductor. Okay? So, what equation can identify, can represent this part or analyze this part of our circuit? What equation, what laws that you learned in electrical circuit analysis could describe the behavior of this part of circuit? If you want to analyze that, like I ask you, okay, this is your circuit, not the other part, only the one within the red line, okay, and analyze it. What you do first to analyze it?
Represent that like a complex number.
We are talking about time, so no complex. We are in time domain.
So what exactly are we looking for, voltage?
Anything, it doesn't matter what you're looking for. I gave you a system and I'm saying, okay, do the full analysis. The first thing that you use in electrical circuit analysis that you learned to analyze this part, what it should be. You have this circuit, V of t, E of s, and you want to analyze it. What is the first thing you do? You're overthinking it. It's very simple.
Label the control.
KVL. It's a circuit. It's one loop. Run a KVL. Now, in a time domain. If you run a KVL, what you're going to end up? You have VT, you have RI, you have the voltage across the L, which is LDI dt, correct? And you have your VFS. And now you have your KVL. Ta-da! That's how ODE of this system would show up. Is KVL. When you look at this damn differential equation, any how you would think of KVL, would it appear to that this is a result of KVL? No, but that's simple. That's simple. And this is how the equation that describes the dynamic of your system. Okay, we draw it, we get it from the KVL. Now, we wanted to like look at it in a better way or simplest way. Okay, when we talk about the V of t, this part is the system. It's gonna be it. We can change it. It's the characteristic of a system. What we have is our V of t and Vs. The V of t is a time varying function which change with the change in the S function, which we basically don't know the actual function. Like when you wanted to like do a differential or integral, if it's a sinusoidal, you could easily take an integral of sinusoidal. But how you wanted to do an integral or differential over S1 when it's not a defined, articulated, like a well-defined function. It's a function that it's like haphazard arbitrary function that describes the on and off switches. So you don't have an actual function to describe that arbitrary waveform. What we could do to deal with that arbitrary characteristics. The result of a semi-handsome guy named Fourier, okay, which is a Fourier series or Fourier transform, whatever you want to call it, okay, would help us to represent any arbitrary voltage or waveform as a summation of a bunch of sinusoidal. And we know how to deal with sinusoidal. We learn that and we practice it a lot. So we are gonna take advantage of that guy's invention, okay, the Fourier series. And instead of that V of t arbitrary function, we are gonna represent it with the equivalent Fourier series of that arbitrary waveform. Now, we have, why I have so many typo, I don't know. We have three terms in our equivalent Fourier series. These two terms represent all the oscillations. What this one represents? Could be zero, but what is the general situation? If you want to generally call it something, you have an arbitrary voltage offset, the DC voltage. The DC component or the offset voltage of that arbitrary. So you have a bunch of oscillation, but they are not gonna, if you integral them through the time, they are not gonna add up to zero because they are offsetted with a certain amount. This one represents that offset. This is the average of the voltage. And you all know what is the average of the voltage. If it's sinusoidal, it's gonna be zero. Average of one side. You wanted to like have it in another perspective. Do you remember? I don't know how many of you had the probability course with me. Do you remember when we talk about the expected value of x minus mu, the deviation, the expected deviation? I don't want to bother you a lot. The expected value is basically the mean value of all the observations. Now you have arbitrary voltage. The expected value would be the mean value. So you add everything divided by the number of components that you added up. Okay, in a one sinusoidal, if you add all the points together, because it has half positive, half negative equal to each other, the average is zero. So always the expected deviation is zero. Then you have a pure sinusoid, no offset. If you have offset, now we are talking an expected value. The expected deviation. Are we good? I wanted to just give you another perspective of the idea. So we are going to put the value Vt on that function, okay? And we are going to derive our formula, our dynamic formula that we had from KVL for our system. Now, one last question, and then I'm going to continue next session. You can see that I'm dealing with Vs as a constant number. This is the voltage of your power system. Okay? And I'm adding it actually here into the DC offset too. Any idea why I'm doing that? This is AC system, this is a power system. This is also a time varying system. How come I could do or using what kind of like concept I can deal or like recognize that voltage of system as a DC or as a constant number? Let me give you a hint. When we wanted to like go from time domain to phasor domain, okay? In time domain, we had AM cosine of omega t plus theta. In phasor domain, we have an amplitude and that theta as a phase. What was that amplitude? Go ahead. Anyone remember?
So like AM over square root.
AM over square root of 2. Why? It's RMS. Root means square. If you have probability with me, it's a second moment of voltage, EX2. Okay? So this is AM over square root of 2, RMS value. Using the concept of RMS and the fact that my system is bulk, so it's gonna be constant. There is no much of fluctuation over there. I'm gonna deal with it as a voltage source with a constant RMS. And using that, now that we have a value of RMS, RMS doesn't change. RMS is a constant value. Okay? The Vs of t alternate like a sinusoidal. But the RMS doesn't alternate. RMS is a constant number. Okay? And since it's constant number, I could deal with it as a offset or a DC in my analysis. And only the oscillation harmonics plus the main component would appear in my alternations or like variations. Are we good? Any question? Any questions so far? No? Good. Sorry, I passed over the time. I'm gonna stop here. Next session, we are gonna continue that and talk about the non-ideal situation and PWM, okay? And moving forward to the concept of finishing the concept of R